Alright, so when we are doing our sampling, we indicate that we want to use nearest neighbor, bilinear interpolation, and here there are this minification filter and magnification. Minification is when you need to make your texture smaller than, I mean, you are not doing resampling in a larger case, when you're trying to map your texture image to a smaller primitive. That's what you want to you're minimizing your texture, and you're magnifying your texture when you try to map a texture to a very large primitive. So sometimes this minification and magnification is better to use different resolutions of the same texture and map it to the appropriate size primitives by finding whether this texture is suitable for this one and this one. OpenGL provides a mechanism for that. This concept is called MIP mapping, to basically create multiple resolutions of your same texture and mapping it to primitives of same size in screen space. Okay, so when I say the primitive size, the size is computed roughly on the screen space. So here, when we are mapping a texture to a polygon of roughly the same size, the result looks really nice. But when we are getting a polygon to a larger rectangle, as you can see, your texture is stretched and its resolution, I mean, especially it's going to be the effects is going to be very bad when you're trying to map it to a very large rectangle in the screen space. And this is when your texture is minified when you're mapping to a smaller rectangle like this. So in minification, a change of 1 pixel in the image space may cause a change of more than 1 pixel in the texture space. So we may need to skip certain pixels in the texture space like this. So there may be some artifacts at this minification process. The same happens at magnification. Your magnified image, even if you're using bilinear interpolation, it's going to get blurred. If you're trying to map a texture to a very large screen space object, it's going to appear as blurry because its resolution does not have those details. Okay, so there will be some effects that occur due to that. There are different ways in animation to fix these effects, which is called, some of them are this changing of pixel coordinates differently than the object image coordinates will cause some aliasing. So we can solve this by trying to map high frequency texture at very low frequencies. These effects will occur. So our sampling rate should be different and different size textures. Okay, so MIP mapping tries to solve this problem, as I said before, by creating multi-resolution textures for the same texture image, large resolution, smaller, and this OpenGL does that automatically for you. There's a function called generate MIP maps, in which we can your texture is pre-filtered to have that and stored in the texture memory beforehand in the pre-processing stage like this. So this is in GL text image 2D. You can generate different levels, and for each level you can store the image differently. So this is doing it custom filtering, but you don't need to do it custom. As I said, OpenGL provides you an automatic way to do that. After you send the highest resolution version of your image, when you say GL generate mipmap, GL texture 2D, and automatically low resolutions of your texture will be created. And in order to use the mipmap images for minification or magnification filter, we have to also indicate use GL linear, but mipmap linear to use a corresponding mipmap image. Just know that we're not going to cover the details of this mip mapping, but just know that using multiple resolutions of the same texture is possible for mapping the texture to different size objects on the image space. Okay, so that's all I want to talk about MIP mapping. Just remember this image. when we talk about mip mapping. But here's also the memory it's going to require every time we are doing the mip mapping. As we reduce the size of the resolution, by default it's always reduced by half each side. So when each side is reduced by half, as you can see, we are reducing the texture size by 4 because it's for 2D textures, and the total size that it's going to occupy is going to be roughly, so this goes all the way to when the smallest texture you're going to get, whatever the size of the single side is, log base 2 of that is going to be. Oh yeah, this is very analogous. Yeah, you're right, Mujella. This is very level of detailed. So the same thing we can do for meshes, for triangular meshes. We can also have different resolutions of triangular meshes, and we can load different versions of them as that triangular mesh goes away from the viewer. We may instead of using the high number of triangle version when it's very small, map to a projected onto a screen space, we may preferably we would want to use just a small triangle version of that. That's the exact same idea, which is called level of detail in meshes, and the mip mapping idea is exactly the same. And this one, just know that, I mean, it's by default we halve the texture size at each step, and this goes until we have one by one pixel, which we will get to in log base 2 n, where n is the length of the original resolution of this image. Okay, if it's not a square image like this, you're going to get the pixel size 1 in one dimension, whichever one of these dimensions is smaller. Okay, I think that maybe one of the reasons in the earlier versions of OpenGL, only texture resolutions of powers of 2 were allowed. This is not a restriction anymore, but I remember 20 years ago, when we were using OpenGL, if you're going to use a texture map, its resolution had to be a power of 2, but it's not like that anymore. Any texture resolution is allowed. Now we're going to talk about frame buffer objects. Frame buffer objects are these rendered images which are not directly displayed to the user, but written off screen into a frame buffer, which can be treated as a texture image and queried as a texture image by using texture functions. Okay, so let me show you 2 examples of that directly. So GLFE examples. I have this depth as texture. So this is a really nice example which shows you. Well, you're welcome, Mujella, by the way. So this is depth as texture example. Let me. Yeah, I already compiled it. Let me show you how it looks like. So this is a really advanced type of functionality in OpenGL actually, which uses this frame buffer object idea. So frame buffer objects in action, you can see it in this spheres.c program. Okay, so I did this for my shadow mapping for my shadow mapping implementation, my own implementation. This was like a debugging program for me. I wanted to see whether I get the depth buffer. So you remember, for each the depth buffer algorithm during a forward rendering pipeline, for each frame buffer, the color buffer, we also have a depth buffer which indicates the depth of the object that is drawn, the closest of the depth of the closest object that actually updates the color buffer. So I wanted to see whether I can get this depth buffer into a frame buffer object and display it as a texture image in an OpenGL program. So this spheres exactly does that. So if you run this, so what you see here is actually you're looking into a 3D scene, but here remarkably this really high frame rate per second. So every time you hit the keyboard R, the spheres are going to start jumping from top. But the main OpenGL program just contains a single quad. Okay, so this window we're looking at is not a window, it's just a quad. And this quad has nothing but a texture mapped onto it. But the texture itself is dynamic. So the texture memory and GPU accessing this texture memory is very fast. As you can see, it's like you can show a movie as a texture by updating your texture at every frame, and it can be updated very fast. So what you're seeing here is this grayscale image is actually the values of the depth buffer. As the objects get closer to you, they become darker. So darker objects indicate here closeness to the camera. Lighter objects indicate they are far away from the camera. So as you see, and there's some scaling to this because between 0 and 1, it's not directly from near to far plane, but I scale it to some values. We can look at the vertex shader for that. But here the depth buffer is rendered as a texture object. So this is an example of a frame buffer object. As frame buffer objects, we can also get the color buffer as a texture. You can get the color buffer, the depth buffer, and render it into an off-screen, and I use that off-screen texture to display it as a texture mapped image. What we do in shadow mapping algorithm, for example, is not to display this depth directly to the user, but we use these depth values in an algorithm to determine whether an object is in shadow or not. Okay, so basically what we do is we render the scene from the point of view of the light source, so anything the light sees shouldn't be in shadow. So what is in shadow mapping algorithm? If there's an object that the light cannot see from this point of view, that object should be in shadow. And how do we determine that? We actually, whatever the object the light sees, its depth is written, its distance to the camera is written in this depth buffer. So what we do is we check the depth of an object from the light's perspective. If that depth is larger than what is in this depth buffer, then that object should be in shadow. So if you see the scene from a different perspective, the camera's perspective, not the light's perspective, we are going to be seeing an object, and we check this object's depth. If it were to be seen from this from the point of the view of the light, and we check that depth to the one that is stored in this depth buffer. If the depth buffer value is smaller than whatever we have for that other object, it means that that other object actually is behind some other object from the light's perspective, and hence it should be in shadow. So I tried to explain the shadow mapping algorithm in a couple of sentences, but we're going to see the details of that probably on Thursday, because I think the remaining of the 25 minutes today I will spend on frame buffer objects, but we may start the shadow mapping algorithm. But I just indicated what shadow mapping algorithm is. So the depth buffer, I also use it for something else. So this, if you look at this other example, the terrain visibility example, yeah, so my mistake last week was not to give this terrain data. So we have a height map in this terrain example, terrain visibility. This height map I actually downloaded from USGS, US Geological Survey. It has the height map of the entire world. So you can get the height values at, I think it's 100-meter resolution. So every 100 meters it gets a height value. It's a regular grid. So when you download it and convert it to an ASCII file, it looks like this. So these are, I think maybe they're in meters. It has a certain resolution, but I have every line contains, every row contains a series of height values. Okay, so this is a real terrain of some place in Turkey. I'm not sure where it was. Actually, I think it's written here in the file name. So north 38, east 36. So it's the latitude, longitude, I think, that type of thing. North 38, so it's the latitude, yeah. East 36 is the longitude. So if you run this program, this is the terrain, okay? So this is, you can look around, and you can actually, so this AWSD keys, they have you look down, look up, and with U you can go forwards, J you can go backwards. So I mean, it's all keyboard movements, so it's really difficult to navigate within this terrain actually. So I'm trying to go backwards. So one thing that is interesting here is this red sphere here actually simulates a different camera than the one that we're currently looking at right now. And the red regions here are the regions in which this camera sees. For example, the green part here that you see here, the green parts in these hills and valleys, means that if we had placed our camera here, we wouldn't see this spot. The red ones are the parts we are seeing. Actually, this is, as you can see, we are looking this way like this. If you're just standing just beneath the camera, you will remain invisible to this viewer here. This spot right beneath the camera, we don't see that. If you just move our camera directly close to that one, we'll see everything we see will be red. I mean, it will be really difficult for me to do exactly come here and turn right. So it's like trying to land a plane in an airport. Oops, yeah, and yeah, the user interface, the interaction is really terrible. Yeah, but yeah, almost. Yeah, if you look at this scene, as you can see, it's almost all red. I'm not exactly in the same spot of this camera. It has some kind of a field of view like this, so maybe a little bit down. As you can see, it's something like this in which we see where we see. So where the camera sees. So if you go above like this, as you can see, there are places where this camera doesn't see behind those. So it's a really nice application of where, for example, these parts here the camera doesn't see. So this looks like an advanced application, but it's really simple. It's the same as that shadow mapping algorithm. This is a light source. These are like this is like an anti-shadow algorithm. The parts that are not in shadow are indicated as this red color. The parts that are in shadow are given the original terrain color according to if there was a light source here. Okay, if this was a light source, this will be like the inverse of that shadow mapping algorithm, and it's really very fast and dynamic. We can actually move our camera. This red and green colors, as you can see, they're computed on the fly dynamically. It's not a texture that is fixed. I can actually move it back, forward, and there are some hill regions down. As you can see, these parts, as I'm moving it backwards, these parts are not visible to this camera. These parts are not visible. These parts are the cameras. And this one uses frame buffer objects to get again the depth buffer. First, I render at each frame. I render the scene from the perspective of this sphere here. And then that view is actually not shown to the user. As you can see, we are looking at the scene from a different point of view. So this we do this by using frame buffer objects. The rendering of from the point of view of this sphere is not done on the screen. It's done on the frame buffer object, and we are not using the algorithm uses not the color buffer of that frame buffer, but the depth buffer of that one. So when I'm rendering, for example, let me get my annotation on and use this blue color. Okay, so when I'm rendering from the point of this camera, which generates this current image, for this pixel here, for example, for this terrain point here, I make this question. For example, let's call this vertex V. So I'm actually talking about the shadow mapping algorithm again, quickly. So let's call this vertex V. It has original coordinates that what we do is in order to see this vertex projected on this position on the screen, what we do is we multiplied it with a modeling matrix, a camera matrix, and a projection matrix, right? This vertex is processed, multiplied, so that we see it at exact pixel location in this image that you see here. Now, what we do is, what if I save a different, let's call this L, let's call this object L. Now, the modeling camera transformation and projection transformation from the perspective of L. What will happen if I multiply this with this V? The coordinate that I'm going to get will be a different coordinate, okay? So this one, for example, let's call this pixel XY. This will be a different pixel, for example, they will be XL, YL. Okay, now what I do is, from this perspective, whatever this pixel XL, YL is, actually it's not this vertex that changes the color of that pixel coordinate XL, YL. It's actually probably there's some other object, there's another vertex somewhere here, let's call it the other vertex, which actually the light sees instead of this one. If these two vertices, they project to the exact same XL, YL, this one is the one that the light sees, okay? Now, but what I get is, by multiplying the same vertex with the projection camera and modeling transformation for the light's perspective, I actually figure out which pixel it falls onto from this perspective. So what I do is, I look at the depth value at this XLYL location. If the depth value at this XLYL, since when you transform this vertex like this, it also contains projection, right? Which means that I also know the depth of this vertex. The depth of this vertex from the perspective of the light will have some depth value. That the Z value of this, the Z coordinate of this transformed vertex will be its depth. So this depth is checked against the one that is stored in the depth buffer from the light perspective. As you can see, what I will suspect here is that the depth buffer, the Z coordinate of this vertex as projected from the light's perspective, this is going to be larger than what is stored at the depth buffer at that XLYL location. And hence, there is some other vertex that is actually that updated frame buffer. So therefore, this one is not seen. Okay, and therefore, this is the exact same idea is used in the shadow mapping algorithm. If this was a light source, this part of the terrain will be in shadow. The light rays will not reach. So light rays is just like line of sight. Okay, if it's a point light source, obviously. We're going to have shadow mapping, assuming that we have point light sources, which only, like, it's like there will be like spotlights, because we will have some kind of a field of view for the light source. Okay, it's not going to be, you're not going to be interested in different places. For example, it will be really bad to have a light source in the middle of the scene for shadow mapping algorithm, because these parts, all these parts will be treated as if they're in shadow. So it's more like a spotlight of like a direct, there's a light source which only illuminates this area, which is shown in red here. Or if you have a light source which is actually at the top, very far away from the scene, which sees your entire scene, then that will also not be a problem in shadow mapping algorithm. But what I want to say is that we are going to, the line of sight of the light rays is the same as to indicate whether a point is in shadow or not. Okay, so that's the shadow mapping algorithm explained in detail. And by the way, there are 2.8 million triangles, so it's really really efficient. The GPUs, I mean, this will be impossible to render it like this in this smoothly. There are more than almost 3 million triangles in the scene, and we are smoothly flying over this terrain. Okay, So how do we do this frame buffer object? The rest of the slides are again like an API reference to tell you how you can create a frame buffer object, how you tell OpenGL to render to the frame buffer object, and you can see the examples again in these two files. The terrain visibility, this terrain.c, let me open. So we should have an FBO frame buffer object here. So this FBO is my, again, unsigned integer, which is a handle to my frame buffer object. So how do I tell OpenGL to render to that frame buffer object? So we generate frame buffer, we bind the frame buffer. When we bind this frame buffer, this is the place where we tell OpenGL you're rendering to this frame buffer object. When we say GL bind frame buffer 0, it renders to the screen. So let's see whether that's the case. Yeah, right here. When we say GL bind frame buffer 0, it will render directly to the screen. So this is the only place where let's search for FBO. Yeah, if I want to get the depth image during rendering process, I just say bind this frame buffer FBO, draw the buffer. So currently it's not drawing and reading, so I don't know why these functions are needed at this point, but here's the place where we're doing the drawing actually in these functions. So here, this is GL frame buffer texture 2D. It's like whatever you are drawing in this frame buffer object, treat it as a texture object. This function is basically saying that these will be texture 2D objects that we are drawing, and there are the frame buffer consists of two separate buffers. One of them is the color attachment, the other is the depth attachment. I think you can even get the stencil buffer. We also talked about the stencil buffer, right? So I think you may even get the stencil values, but usually the color values and depth values are used. The color values are used rendered into render texture, and depth texture contains our depth values, and which can be queried as a texture. So at this point we are so the sensor is the light position. So GL, you look at sensor means that get your camera to where that sphere is and see the entire scene from the perspective of that sensor So this is like if we put a sensor in that terrain, where would that sensor sense in the on the terrain? Okay, so we save the model view matrix of the sensor is saved into some variable, because we will need that when we want to query the depth of some particular vertex. We will need the model view projection matrix from the light's perspective, from the sensor's perspective. So this is where we do the drawing. Where's GL draw? Yeah, GL draw elements. So this is the place where we draw the entire scene. So let's get back to this. So we bind whenever we say bind frame buffer, that we say OpenGL draw whatever you're drawing to this frame buffer object. So in order to have this frame buffer object allocated a texture space in the texture memory on the GPU, we need to generate a texture, and then we have to give the frame buffer height and width to this one. So this part is the one where we prepare our texture, and this is the so yeah, here this one is say this is a depth component, and here these are texture preparation steps. These two functions are the actual functions which ties those prepared textures with the frame buffer object. Okay, so whatever the current bound frame buffer is, it connects that frame buffer and its color buffer, its color attachment with this texture ID, color texture, depth texture. Okay, these two functions couple, attach the texture to the objects, to our frame buffer objects. And after all this is done, we check whether frame buffer is successfully created or not by using this GL check frame buffer status to indicate, to see whether it's completely is complete or not, it's created or not. So whenever we want to render to a frame buffer object, we just make sure that it's bound. The texture contents will be updated automatically. Just remember how those jumping spheres, which was a texture, so quickly updated, so smoothly updated. And also, before rendering, we need to make sure that our viewport is also, we should match the resolution of this frame buffer by updating our viewport function like this. And once you make a frame buffer object rendering pass, we can detach our textures and switch back to the default frame buffer. So we can do the detachment, and we can just bind frame buffer 0 to draw everything to the screen. Now we can use these textures as source textures for very special effects, like you can query those to do shadows, or to like the visibility, terrain visibility, to show where a camera placed at this location, where does that camera see. You can do these additional effects at your programmable shaders. So yeah, then generating shadows is what we will learn next. Actually, I finished earlier than I expected, so we can directly start on the shadow mapping slides. I also explained the shadow mapping algorithm, but let's see. So as I said, we are not going to have classes next week. So our last class this semester will be on Thursday. If we cannot finish this shadows, I will have an additional lecture, or I may also give pointers to videos that I had last year. And curves and surfaces, we are going to completely omit them. We are not going to talk about curves and surfaces in this course. You're not responsible for curves and surfaces. If you're interested in this material, I suggest you take also just technical elective course that he will offer next semester, in which he's going to talk about curves and surfaces at the beginning of that Computer Graphics 2 class. Okay, so shadows in forward rendering pipeline. So for quite some time before programmable shaders, we didn't have shadow in OpenGL, which was a great disappointment. These shadows, very nice. I mean, shadows provide lots of realism to the scene, lots of visual cues. I mean, cognitively, when we are interpreting a scene as human beings, we make use of shadows a lot. There are these nice illusions related to these shadows. Other than the shadows, these two images are exactly the same, but with just different shadows. Just look at these two images and see how different we interpret them. In this case, we interpret these balls, all of them are on the checkerboard, at the surface of the checkerboard, because of their shadows tell us that. And here, the same spheres, 4 of them, the same orientation, the same, their rendering is exactly the same. The only thing, as I said, is the shadow that is produced underneath them. We interpret the scene entirely different, and seeing that, oh, okay, these 4 spheres are actually on this row. They are equidistant to the viewer. This one is just above the checkerboard. So shadows are really important clues to positions of objects and to provide realism into the scene. Okay, so an absence of shadows in OpenGL was, as I said, great disappointment, and people use different tricks. This didn't allow graphics programmers, which also they are like hackers, to use the system in different ways, to use the available system and to extend the available system by using different tricks to create shadows. One of those was actually having shadows pre-computed and embedded into the textures that we have, which is called baking the shadow. So you can compute a shadow beforehand and just have it on the texture. This works when your objects do not move, your light sources do not move, but you cannot have dynamic shadows if you have lots of moving objects around, if your light sources also move. Having a dynamic shadows would be really difficult. You cannot have baking and dynamic shadows. Okay, but with the help of programmable shaders, this is possible, as we have seen in the examples, like this terrain visibility example. Just invert that when it becomes your shadow. I mean, invert the red color, make the other parts a little bit darker. It will immediately give you a dynamic shadow. Actually, we could do that quickly. So let me try to just convert in the last 4 minutes. So before going into the shadows, there are some more examples like this. Shadows give important cues about light positions. For example, here the light is probably the same from location as the camera. Here the light is to the left-hand side. And here, as I said, OpenGL does not have built-in support for shadows. Scenes look as dull, uninteresting like this. But when we have shadows, compare this to a ray traced image, looks much nicer, right? Now, let me try to, where's my, it's the GLFW examples 1. So with just very simple modification, terrain visibility. Let's take a look at this. I have this fragment shader. Let's see what it has. Look at this. This R color is the red color. Okay. Now, what we do is, so this is the fragment color. It's either T color or, so if that point is seen, and this scene is actually looking at the texture, it's looking at the depth value, it's checking the depth value of this, it's then its scene is equal to 1. Okay, if the camera sensor sees that, it means it's 1.0. So I'm going to revert that actually. It's like I'm going to do it like this. This is going to be 1.0, this is going to be 0.0. So with just simple immersion, the red places will become green, the green places will become red. So let's see that that's the case. Yeah, you see? So I just inverted what I did here. Now, these parts are actually will be in shadow. So instead of, I mean, shadows being red does not look good, right? So what I'm going to do is this. The red parts, our color is going to be equal to T color times 0.2. I'm going to make it darker. I mean, this is a very cheap trick to have shadows to make the color appear darker. But let's see how it's going to look like. You see, so actually it's too dark. But here, if you see your scene here, this is the shadow mapping algorithm in action. The parts, I mean, if we had a light source here, if this was, imagine this is a night scene, okay, and this is our spotlight that lights this entire area. So these parts will be the parts in which they are not illuminated by the spotlight. So if you move it here like this is like your spotlight. The parts that are not covered by the spotlight are the parts that are in shadows. Okay, so here, I don't know, it's really difficult to move in this lots of keyboard mappings. Yeah. Okay, so this is basically an implementation of the shadow mapping algorithm. We are going to talk about this in more detail on Thursday. So, okay, so the plan for Thursday is to finish the shadows in OpenGL slides, and that will be the final topic this semester. If I can finish the entire set of slides on Thursday, you're not going to have any additional class, and you're other than these. And I may have some kind of a discussion session before the final exam if you need such a discussion session. All right. See you all on Thursday. I will stop right here. I will stop recording now.